Hello. This is our continuation on methods for solving ordinary differential equations. And today we will discuss the use of the Laplace transform for solving linear ODEs. Again, our key reference is the textbook by Boyce and Di Prima, and in the case of the Laplace transform, chapter 6 is the one that covers the topics of today's lectures. All right, so we are going obviously to provide the definition of the Laplace transform and see how it comes to play a role in solving ODEs. But let me just say that the key idea here is we are interested to model discontinuous or impulsive forcing terms. So these are the terms on the right-hand side of the differential equation. And most of the methods, if not all of the methods we have discussed up to now, they're not appropriate for this type of problems. So what we're going to do is we're going to transform the differential equation to another space effectively. So a function f is going to be transposed to another function that we will call capital F. And the transform that we're going to use is going to be an integral transform like the equation that you see on the bottom, using some appropriate kernel k of s and comma t. So f of t, you can think of the solution of ODEs is going to be the solution of the differential equation, and capital F of s is going to be the transform of that solution. And notice the variables. We're going from, let's say, a variable t that can be time to a variable s that defines the space of this integral transform, and in particular of the Laplace transform once we introduce that. So before I say anything about the Laplace transform is going to come to be an improper integral. So let's introduce the concept of improper integrals. And you see here an integral that goes from 0 to infinity. From A to infinity. So effectively, we define this as the limit of this integral from little a to capital A as capital A goes to infinity. And we will work with cases where this type of integrals converge to some limiting value as capital A goes to infinity. And if the integral basically doesn't exist, then and it diverges, it will not be much of use in the context of the transformation methods that we are to discuss today. Okay, so let me consider as an example of this improper integral. So the way you're going to evaluate it is you're going to change the upper limit of integration to some capital A. And once you evaluate the finite integral from 0 to capital A, you're going to take the limit as A goes to infinity and see where that converges. So this integral here from 0 to A looks like 1 over c e to the ca minus 1. And when you take A to infinity, you have to evaluate this term here where A comes. And obviously, the behavior of this term depends very much on the constant c. So if c is equal to 0, you can see that the integral diverges. If c equal to 0, this exponential here is 1. So basically, this integral becomes infinity. So the integral diverges. If c is not equal to 0, and you can integrate because c comes in the denominator, the behavior depends on this exponential. So if c is negative, so immediately you can see as a goes to infinity, e to the minus some big number here will give you a 0. So the value of the integral is minus 1 over c. And of course, if c is positive as a goes to infinity, this integral diverges. So this is how we're going to be computing improper integrals by making them proper integrals with some finite upper limit of integration, and then once the integration is performed, take this upper limit of integration to go to infinity. In some sense, you can be performing both operations simultaneously if you feel comfortable in doing this type of calculations. So let me do another integral. Again, we have infinity on the upper limit, so we're going to change this from 1 to a, and this integral becomes log of a, so we're going to have take a goes to infinity of log of a, and obviously this integral diverges. So let me consider, I'm going to put all of these things up. Let's consider this integral of t to the minus p from 1 to infinity. So if you change the upper limit of integration to a, t to the minus p becomes t to the minus p plus 1 over p minus 1. I'm sorry, over minus p plus 1. So this integration from 1 to a gives you what you see here on the right-hand side. So obviously, as a goes to infinity, the behavior of this calculation depends very much on what's going on with the exponent 1 minus p if it is less or equal to 0. So for the case that p is greater than 1, right? So remember that a is a very big number, a goes to infinity. So in the case of p greater than 1, 1 minus p is negative. So it's like having 1 over a very big number to a positive number. So obviously that goes to 0. And the integral becomes minus 1 divided by 1 minus p, or as I saw here, 1 over p minus 1. And of course, when 1 minus p is a positive number, so a to some positive number gives you infinity, so the integral diverges. Again, that's we haven't really said anything about the Laplace transform, but because the Laplace transform is going to come to be an improper integral, it is a good idea to actually see some of these calculations early on. So let me, in preparation for introducing the Laplace transform, let me define a piecewise continuous function in some interval AB. So here is a typical example of a function that, as you can see, it is continuous piecewise, but has a finite number of discontinuities. For example, as you can see at T1 and T2. So this function is called piecewise continuous. So it's continuous in each interval. And when we look in this particular function here from T1 to T2, notice that the value at T1 plus, so as we approach T1 from inside this interval, the value that we have for the function is finite. And similarly, as we approach T2 from inside, so at T2 minus, the value of the function is also finite. So if those three requirements are satisfied, we call that, we say that the function is piecewise continuous on the interval from A to B. And those, again, will be very much important functions, allowing for the finite discontinuities in the domain, but in between, in each piece, basically, of the discretization, the function we will consider will be continuous. Okay, so we're ready to define the Laplace transform, and we're going to take it to be the integral, the improper integral of e to the minus st f of t dt. We denote the Laplace transform with a capital F of s. So s is our new variable here, so we're going from t to s. And so if you remember the integral transform that I introduced in our most probably first slide, it had a kernel in the integral transform. So the kernel in our case is this exponential kernel e to the minus st. So now if you remember these linear equations that differential equations that we worked, they all had solutions that they were of some exponential form e to the rt. So immediately you can see that this exponential term here, e to the minus st, is going to be very helpful in computing the transform of solutions that have an exponential nature. So in some sense, the Laplace transform would be ideal to work with the solutions of linear differential equations. So let me give a formal theorem for the existence of the Laplace transform. So we're going to take a function that is piecewise continuous from 0 to b, and we're going to assume that in an absolute value, this function is bounded by this exponential e to the at for some time t greater or equal to some reference time capital M. For the other parameters here all being constants, and of course k and m being positive numbers. So we have a function basically that is bounded by an exponential, all right? So the growth of this function is not faster than that of an exponential. And in those cases, the Laplace transform exists for all s that is greater than this a that you have in this constraint that we use for the absolute value of f of t. And actually, you can appreciate without much of a proof that indeed, when you look at this, the calculation of this integral, that this integral exists when s is greater than a, where again a comes from this constraint that we introduce on f. So we're actually going to refer to a function f that satisfies the constraints 1 and 2 on the slide as a function that has exponential order as t goes to infinity. All right. So let me start doing some examples with the Laplace transform, starting with a trivial evaluation of the Laplace transform of a constant function. In particular, here we take f of t equal to 1 for t greater or equal to 0. So if you plug in the transform f of t equal to 1, so you evaluate this improper integral, and you're going to have e to the minus sb, and for s positive, e to the minus sb as b goes to infinity is 0. So what you get from this limit here is 1 over s. So the Laplace transform of the constant function here, in particular of 1, is 1 over s for s greater than 0. Note that this is very important that s is greater than 0, because otherwise we will not be able to say that this limit of e to the minus sb as b goes to infinity is equal to 0. Similarly, let me do the Laplace transform of an exponential of e to the at. So you can evaluate this integral, and when you take the limit of b goes to infinity, you can see that for all s's that are greater than a, similar situation as before, this exponential evaluated at b becomes 0, and the Laplace transform of e to the at is 1 over s minus a. Let me see if we have another example. So here's another example of a function that is piecewise continuous. So you notice at t equal to 1, there is a finite jump from 1 to k, where k is some constant. So if you evaluate the Laplace transform as the integral that you see here, effectively this jump at t equal 1 contributes nothing to the integral. So basically, the Laplace transform comes to be the f of t here takes the value of 1. That's the only thing that is going to give you contribution. But you notice because the function f of t equal to 1 is defined from 0 to 1, I have to change the limits of integration here from 0 to 1. So the result basically comes 1 to minus e to the minus s over s for s positive. We're not really interested on this particular Laplace transform, beyond the fact that I wanted to emphasize that this finite discontinuity here has not contributed at all to the evaluation of the Laplace transform. So it has not changed so there's no k dependence, as you can see, on the Laplace transform. All right, so let me evaluate now the Laplace transform of sine of at. The calculation looks a little bit lengthier, but you have to use integration by parts, so there is really nothing fancy that we need to spend time here. So you have sine of at, and so what basically I can do, I can write the sine of at as minus the derivative of cos of at divided by a, and use integration by parts, and of course take the limits as b goes to infinity. So you can immediately see that e to the minus sb for s positive will drop out, and you will get 1 over a from this integral. And then you have to do one more integration by parts. You notice if you do one more integration by parts, you actually do get the Laplace transform of interest, the Laplace transform of sine at again. So, the contributions from these terms here are equal to 0 because e to the minus sb is 0 as b goes to infinity. And of course, for t equal to 0, the value of sine of at will be equal to 0. So effectively what you get is you get 1 over a minus s squared over a squared, the Laplace transform that you want to compute. So if you put f of s on the other side, you do compute this important result that the Laplace transform of sine of at is a divided by s squared plus a squared. Linearity of the Laplace transform. If you know the Laplace transform of two functions and then you take a combination of them, then the Laplace transform would be a combination of the Laplace transforms of the two functions. So if you are looking for two functions f and g, and you try to compute the Laplace transform of c1f plus c2g, then that Laplace transform is nothing else but c1 the Laplace transform of f, and c2 the Laplace transform of g. So the Laplace transform behaves linearly, and of course this is a useful statement to use in calculating, for example, the Laplace transform of this function that you see here. So you have two combinations here of e to the minus 2t and sine of 4t. So effectively, if you know how to compute the Laplace transform of e to the minus 2t and the Laplace transform of sine 4t, then you can immediately see that the Laplace transform of this function is 5 times the Laplace transform of e to the minus 2t, which is 1 over s plus 2, and the Laplace transform of sine of 4t, which is 4 divided by s squared plus 16. So 4 times 3 gives you 12, and there is the answer. Obviously, we said we will use the Laplace transform for solving initial value problems. So the question is, how is this going to come to play a role? So to be able to actually use the Laplace transform for solving initial value problems, we need somehow to be able to compute the Laplace transform of the derivatives of a function f of t. And so let's see how this comes up. So that we will see in this slide that computing the Laplace transform of the derivative of a function of t, it's a trivial task. And as this formula shows here, the Laplace transform of the derivative is s times the Laplace transform of f minus f of 0, which is the initial condition on f. Again, this is for s greater than some value of a. And we have the usual constraints to make this to work. F needs to be continuous now, and f prime, the first derivative of f, needs to be piecewise continuous on some interval from 0 to b. And then f of t needs to be bounded by this exponential function k e to the at. Okay, this is very important. And once those two things are satisfied, then the Laplace transform of the derivative is s times the Laplace transform of f minus f of 0. The proof is actually rather trivial. You know, you can evaluate the Laplace transform of the derivative by performing integration by parts. And the first term, you can see as b goes to infinity will drop out. And then from the second term here, you will get minus f of 0. And this last term is, as b goes to infinity, is the Laplace transform of f. So that's very nice. And again, we need the only constraint in addition to what we had before is that f prime needs to be piecewise continuous to allow this type of calculations. So this idea now with the first derivative and the Laplace transform of the first derivative, you can extend it easily to the second derivative by amending the previous theorem. So the Laplace transform of the second derivative is s times the Laplace transform of the first minus the initial condition of the first derivative. So this is exactly what we had before, which is the equation on the top, but now I apply to the second derivative. And here I can substitute now the Laplace transform of the first derivative, and then you get that the Laplace transform of the second derivative of f is s squared times the Laplace transform of f minus f times f of 0 minus f prime of 0. So you can see how naturally the initial conditions are coming in the Laplace transform. And as a matter of fact, you can notice the initial conditions are enforced directly in evaluating the Laplace transform rather than at the end once some particular solutions to this differential equation have been computed the way we have done this in the past. And I'm going to show you an example of this shortly. So you can actually evaluate, derivatives of any order, and you can see on the slide here at the end, I have the Laplace transform of an nth order derivative. So the leading term again is s the power n of the Laplace transform of f, and then you have the initial conditions up to the n minus 1 derivative at time 0. And the only requirements that you need to enforce here is that all the derivatives up to order n minus 1 need to be continuous. The nth derivative needs to be piecewise continuous for the Laplace transform to exist. And then you need to have the absolute values of f and all the derivatives up to n minus 1 to be bounded by the same exponential e to the at as we have seen in the earlier slides. So let me do an initial value problem, first starting with things we already know. So if you try to solve this problem, you will look for the characteristic as solution. So you take e to the rt, plug it in and get a characteristic equation, which is a second order polynomial. So here it has solutions r equal 2 and minus 1. So the general solution looks like this. And then you go as a post-processing, if you like, and you apply initial conditions that y at 0 is equal to 1 and that the derivative at 0 is equal to 0. And that allows you to compute the coefficients. And here is the solution. This is how we used to operate with initial value problems. Now, if you try to do this with the Laplace transform, you would start taking the Laplace transform of the differential equation. So we have Laplace transform of y double prime minus the Laplace transform of the first derivative minus 2 the Laplace transform of y. Obviously, we have used here the linearity of the Laplace transform, and the Laplace transform of 0 is equal to 0. Substitute what we already learned from the theorems for the Laplace transform of the second and first derivative, and plug in the initial conditions on y0 and y prime of 0, and solve for capital Y of s. And here's the answer. So we get that the Laplace transform of the solution to our problem is s minus 1 divided by s minus 2 s plus 1. So now we have, of course, the difficult task of computing the inverse transform of this. So we are going to obviously use some tables of Laplace transform to compute the inverse transform using the inverse transform of some very basic functions. So the first thing you need to do is you need to use partial fractions, and you need to effectively write this. This is our Laplace transform. Write it as some constant divided by s minus 2 and some constant divided by s plus 1. I am sure you know how to compute a and b, and the algebra is shown on this slide. So if you compute a and b, this is what you get. And now you need to compute the inverse transform of this. And of course, you know that the inverse transform of, you know what gives you s minus 2, and you know what gives you s plus 1. Okay, so let's put this thing up. So so we had 1 over s minus 2. So obviously this leads to an exponential, which is e to the minus 2t. Okay, I'm sorry, e to the 2t. Okay, and then here we have s plus 1. This leads to an exponential, which is e to the minus 2, e to the minus t, using this the equation that you see on the top. So effectively, immediately you can recognize that the function of interest, the solution to the initial value problem, is nothing else but 2/3 of e to the minus t and 1/3 of e to the 2t. And try to appreciate the fact that the Laplace transform gave you the solution, and the initial conditions were accounted directly in deriving the Laplace transform, rather than at the end by sort of computing fitting constants so that they managed to give us the initial conditions. So it's a little bit of different from what we have seen in the solution of ordinary differential equations. All right, let me do another example. So let me take a more general second order differential equation. So this can be like a vibrations problem with f of t being a forcing term. So if you take Laplace transforms for a, b, c being constants, and you obviously need to evaluate the Laplace transform of the right-hand side. So you put all of this together, and then at the end of the day, with some initial conditions on y0 and y prime of 0, the Laplace transform of y comes to be given by this equation on the bottom. And a comment here, you notice that the Laplace transform, what you get on the denominator of the Laplace transform, it's really the characteristic polynomial of the ordinary differential equation. And we're going to have to use these partial fractions that we did in the earlier example. So you can appreciate if you have a high-order differential equation, you're going to have to find the roots of the characteristic polynomial, which is not an easy problem. So in some sense, the Laplace transform for higher order differential equations may not be as useful as we make things to look like in this presentation. So maybe the potential of the Laplace transform on higher order differential equations, it doesn't look as good simply because of the need to evaluate the roots of this denominator so you can do partial fractions. So So we're going to have to do partial fractions, and if you can, and in this case, the problem looks rather simple. You'll be able to invert and compute a solution y of t for this particular problem. And again, notice that the Laplace transform, the solution involves directly the initial conditions. So the initial conditions have been taken care of in the calculation of y of s and do not need to be enforced separately at the end. So again, this is the same problem that we had. And so what I'm going to do is, let me see if we have an example for this second order equation. Actually, I don't see yet an example on this. Okay, so I think the slide again makes the point that we need to find the roots of alpha s squared plus bs plus c. And for a second order equation, it's always simple. For higher order equations, that is a problem. Let me say something about the Laplace transform and the inverse of the Laplace transform. In some sense, if we start with a function, we can compute the Laplace transform, and we have seen in the solution of the ODEs, we need to solve the inverse problem from the Laplace transform. We need to compute the function. So the notation here is we apply the inverse Laplace transform to allow us to do this. If the function f of interest here is continuous, you can actually show that when you compute the inverse transform of capital of f of s, then you do get a unique continuous function from that inverse transform. So basically, when you take the inverse transform for continuous functions, the answer is unique. You will see in textbooks lots of tables of Laplace transforms, and here is a summary of some basic ones. You don't really need to memorize those. Of course, when you do the homework, you will remember this for a day or two. After that, you need to consult a table so that you know the basic functions like monomials in t or sines or cosines or hyperbolic sines, or even the product of these exponentials times cosine. You should be able to use these tables to evaluate the Laplace transform. And more importantly, when you use the partial fractions idea, you should be able to go backwards from the Laplace transforms that take any of these forms in this table. You should be able to go back and compute the unique function that leads to those. Now, if you remember, we stated before that the Laplace transform is linear. So if you take combination of functions, their Laplace transform is a linear combination of their Laplace transform. The same, of course, is true for the inverse Laplace transform. So if you have to compute the inverse transform of a combination of functions, you can actually take the linear combination of the inverse Laplace transform of each of them, and that is indicated in the equation on the bottom. And of course, with confidence, you can say if we are dealing with continuous functions, that the solution to this inverse transform gives you a unique function f of t. All right, so let me do an example of a second order problem. So it's an initial problem with some specified displacement and velocity. If you take the Laplace transform, evaluate the second derivative, the Laplace transform plus L of y, and the Laplace transform of the sine of 2t is 2 over s squared plus 4. So plug in the initial conditions and solve for your Laplace transform. You get this expression that looks complicated, so we're going to have to use partial fractions to be able to identify the inverse of this. So how do the partial fractions are going to look like? We're going to write, because this is a third order polynomial, we're going to need linear functions of s in the numerators and quadratic, of course, in the denominator. So from this, you can, if you multiply as plus b with s squared plus 4 and s squared plus 1 with cs plus d, you can put this equal to this expression, the numerator, and then try to match all the coefficients of s, of powers of s. And here's the answer. If you do all of this, you get something like that. And immediately from this, you can use the linearity of the inverse of the Laplace transform. So obviously, the inverse of s over s squared plus 1 is cosine of t. And so you're going to get 2 times cosine of t and 5/3 sine of t and minus 2/3 sine of 2t. And that's the solution to our problem. We can even try a fourth order polynomial that will not be painful to compute the roots of the characteristic polynomial. So obviously here we need initial conditions up to the third order derivative. If you take the Laplace transform of the fourth derivative minus the Laplace transform of y equal to 0, put your initial conditions, solve it, you're going to get some capital of y to be s squared divided by s squared minus 1 times s squared plus 1. So obviously we're going to have to use partial fractions, and exactly as before, the decomposition is going to look as you see on this slide. And you can evaluate the constants a, b, c, d the easy way or the hard way. The hard way will be to multiply as plus b with s squared plus 1 and cs plus d with s squared minus 1 and match all the coefficients with those of s squared. Or the other case would be to use, rather than expanding this in powers of s, you can actually, if you plug in s equal to 1 and s equal to minus 1, this term drops, and that will allow you to compute a and b directly. And you can do similar calculations to find c and d. So let me just give you the answer. The partial fractions expression is 1/2 of s squared minus 1 and 1/2 of s squared plus 1. Now, if you look at the tables, 1 over s squared minus 1 is the Laplace transform of the hyperbolic sine of t, and 1 over s squared plus 1 is the Laplace transform of the sine of t. So the solution to our problem is given as the 1/2 of the hyperbolic sine plus sine of t. And there is a graph here. This is how this solution looks in this particular case. All right. I mentioned very early in the lecture that we're really interested in Laplace transform so we can work with discontinuous forcing terms and impulsive forcing terms. So I need to say something about the use of step functions. So let me proceed and define the step function that you see, uc of t, as, let me start with a graph first, is a function that is 0 before c. C here, I'm taking it to be a positive constant, and it is 1. This function is 1 for t greater than c. So the function is given by this. So we're going to use this compact notation uc of t to indicate this unit step function. So this step function is 1, but for t greater than c. Okay, so this would be my definition of the step function. So if I ask you, let me just put this picture here, to write down this function, which is a negative step of value 1 in terms of the unit step function. Obviously, this function here is 1 for t less than c, and it is 0 after that. So you can think of an easy way to represent this is to write it as 1 minus uc of t. you can see that for t less than c, uc of t is equal to 0. This is what we had before. And after that is equal to 1. So 1 minus 1 equal to 0. So this is a negative step function. Now, with this step functions, you can do lots of fancy things. So, for example, if you want to write down a function that takes the value 1 between pi and 2 pi, all right? A function that takes the value 1 only between the values pi and 2 pi, and it's 0 everywhere else. You can actually write this as the step response u pi of t. So this will give you 1 after pi, but because you want 0 after 2 pi, you're going to have to subtract the function that gives you 1 after 2 pi. So you can again see that this compact notation here represents this rectangular pulse between the values of pi and 2 pi. Okay, so let me do another example. How about this function? How can we use this step function to describe this interesting function that has the value 2 until the time 4, then jumps to 5 until time, 7, and then at 7 it goes to -1, and then at 9 goes to +1, and then it remains, I suppose, at that value after time t equal to 9. So how do we express this? And here's a compact way of doing it. So let me go directly on the result. So obviously you have 2. You start with 2, all right? Suddenly, this thing has to jump and become 5. So you're going to add 3 u4 of t, okay? So 3 and 2 will give you 5. Then the function has to drop by 6 at time t7. So we're going to subtract -6. And then it has to grow by 2, and this is the general expression, the compact notation for this combination of step functions. And again, you may say, well, how is that going to help me? Well, if we have forces that change with time, the way this particular function h of t is in this example, we're going to be able to evaluate the Laplace transform easily, because the Laplace transform of the step function will be something that is going to be extremely easy to evaluate. And I'm going to actually do this, I think, next. So let me do the Laplace transform of the unit step function uc of t. So you remember this function is equal to 1 for t greater than c. So my integration will change to c to infinity, and the argument inside here for uc of t, I'm going to have 1. So when you evaluate and you take b going to infinity, you come up that the Laplace transform of a step function is e to the minus cs divided by s. This formula is so fundamental, of course, is given in the table of the Laplace transforms of usual functions that we have to deal with. So again, you don't really have to remember this, but remember that there is a nice formula that you should look for the Laplace transform of the step function. Let me do something very interesting. So let me go on this picture first. Suppose you have this function f of t that starts with this value f of 0, and you want to translate this whole function by a time interval of c. So we want basically to keep the same identical function, but translate it by a distance c. The question is, what is this new function? Well, the new function is, if you try to visually represent this, to mathematically represent what you see here visually, is a function that is 0 if t less than c. And of course, for t greater than c, the function is f of t minus c. Right, so you just have changed the time from t to t minus c, and the value of f remains the same. So can we compactly write this function? Yes, we can. So g of t is f of t minus c times a unit step function that forces this to be 0 for t less than c, and after that is equal to 1. So after that we get f of t minus c. So here we have the product of a step function with f of t minus c, and this is a good way to write compactly the translation by a times c of the function f of t. And again, no surprise that the Laplace transform for what you see here, it's easily computed, and it's actually something that you will see in the previous table that we had. So let's calculate this. So if you want the Laplace transform of this, so the Laplace transform is actually given, let me just put the answer, is given as e to the minus cs times f of s. So effectively moving the time by the interval c, it's equivalent to multiplying the Laplace transform of f of t with e to the minus cs. And of course, here we take that this time interval c is greater than 0. Now, you can also do the inverse of this. So, you know, if you have a situation of that you need to compute the inverse transform of e to the minus cs of f of s, then the answer is not anything else, but it is the function f translated by a distance c in time. So, and that, as we know, is given by this nice expression uc of t f of t minus c. So let me actually prove all of these things. You know, so we want to prove first this. The answer, the proof is relatively easy. So this is the definition of the Laplace transform, and remember, this is 0 for less than c, so the integral changes, the integration changes from c to infinity. And literally, to compute this integral, what you need to do is you need to change variables. So if, instead of integrating in t, define t minus c to be u, move e to the minus c outside the integral, and immediately you can see the Laplace transform of f. So effectively, the Laplace transform of this shifted function of f by this distance c is e to the minus cs times f of s. So let me do an example. Let's suppose that we want to find the Laplace transform of this function. Takes the value sine of t between 0 and pi over 4, and sine of t and cosine of t minus pi over 4 after that. So you can write this in a compact way as sine of t plus u, the step function for a constant pi over 4. And if you try to take the Laplace transform of sine of t is 1 over s squared plus 1. And here, what you have is you have the Laplace transform of the cosine of t that has been shifted by pi over 4. So you're going to get e to the minus pi s over 4. And then you have the Laplace transform of the cosine of t, which is s over s plus squared plus 1. And immediately you are done with this. And you can do the inverse, of course. And here is another example. If you want to compute the Laplace transform, the inverse Laplace transform of what you see here, you obviously are going to have to compute the Laplace transform of 1 over s squared, which is t, and then the Laplace transform of e to the minus 2s over the inverse Laplace transform of e to the minus 2s over s squared. So you can see you multiply 1 over s squared by e to the minus 2s. 1 over squared has an inverse Laplace transform, which is t. So really the answer is nothing else but t shifted by a distance 2. So this is what you get. And if you expand this, you know, for t less than 2, the second term is 0, so you get t. For t greater than 2, this is 1, so you have t minus t cancelled, so you get 2, and that's the answer to the inverse Laplace transform. This is a very important theorem, right, that we're going to use often in our calculations. So if you have the Laplace transform, this is another theorem, by the way. This is not exactly what I was referring before. So if you multiply a function by this exponential e to the c t, this is the same as shifting now the Laplace transform of the function f of t. Okay, so multiplying e by ct. So in the time domain, you multiply by e to the ct. In the Laplace domain, you're actually what you do is you shift the variable from s to s minus c. And the inverse, if you have to evaluate the inverse Laplace transform of f of s minus c in the time domain, this is the same as multiplying by e to the ct. So this is as powerful as the previous theorem. The proof again is rather trivial. You can see here, if you take the Laplace transform of what you need, e to the minus st times c to the ct. So if you combine the two exponentials, immediately you can see that this is multiplying by e to the ct in the time domain is the same as shifting by c in the Laplace domain. And we can use an example of this if you want to compute the inverse transform of this term here, 1 over s squared minus 4s plus 5. You can actually, with simple manipulation, you can write this as 1 over s minus 2 squared plus 1. And it seems to me this is immediately the shifting by 2 of the Laplace transform of 1 over s squared plus 1. Immediately we can see that the inverse Laplace transform of this will be e to the 2t times the Laplace transform times the inverse Laplace transform of 1 over squared s squared plus 1, which is sine of t. So basically our answer is e to the 2t times sine of t. So again, you can see shifting in the Laplace domain by a constant c implies multiplying in the time domain by e to the c ct, and similarly for the inverse, here multiplying by e to the 2t in the time domain, it's equivalent to shifting in the Laplace domain by the value of 2. All right, so I'm going to stop here, and we're going to continue in our next lecture with more applications of the Laplace transform to differential equations where we have discontinuous forcing terms, and see how we can take advantage of these theorems that we learned in the lecture today to solve such type of problems. So I will see you in the next lecture. Bye.